This lesson is taking a look at solubility and intermolecular bonds. Polarity allows molecules to blend in, or in biochemistry, meaning to dissolve. So whether a molecule is polar or nonpolar will dictate what it can dissolve in. So we start off with the rule of solubility. The rule of solubility is simple. Like dissolves like. So we've all seen oil floating on top of water and know that no matter how much we mix it up, we shake it up, it is going to separate out. The reasoning is water, as we saw in the last video, is polar. Oil, on the other hand, is non-polar. So when you have something that is polar and non-polar, they will not stay mixed, they will not dissolve, therefore they are not soluble. So polar molecules will dissolve in water, non-polar molecules will dissolve in oil. So hydrophilic, another word for water-loving compounds, will dissolve in water because they're polar or charged and can form intermolecular bonds. So let's take a look at salt or sodium chloride down here. Now these ions are positively and negatively charged, meaning that they attract the dipoles of the polar water molecule. So the chloride ion attracts the hydrogen of the water and the sodium cation attracts the oxygen. Now water can make those bonds, therefore separating them, which is essentially all dissolving or solubility is to separate or to disperse a substance. Now if we look at a larger molecule like a glucose, it has polar sections which the water can cling onto as well, which can use to separate it. Even though it's not broken down or dissolved into its individual atoms, it is separated as a molecule. So salt, the dipoles of water attract to the charged ions, whereas in sugar, dipoles from the polar molecules attract to each other. Oppositely, hydrophobic or water-hating compounds do not dissolve in water because they are non-polar and water can't bind to it. So if we take a look at gasoline or hexane, because of its linear symmetrical shape, it is a non-polar molecule, meaning that water has nowhere that it can attach to. There are no little positive or negative dipoles that water can use to separate those molecules. That's why when you see an oil spill, the oil just floats on top of the water because it can't blend in. It is not soluble in water. So gasoline, non-polar compound of carbons and hydrogens. Non-polar means that it will not dissolve in something that is polar. We can always appreciate a good biochemistry joke or two, so take a second, laugh away, and let's return to the note. So we're going to take a look at some even more bonds, more chemical bonds, but this time intermolecular bonds, meaning between different molecules. So the first type we're going to look at are hydrogen bonds. As the name implies, there must be a hydrogen involved. So they're relatively weak forces between a polar molecule and a hydrogen of another polar molecule. And it's due to their dipoles. So if we look at this example down here, we have water with the slightly negative oxygen, and we have this slightly charged hydrogen over here. They are going to form a slight attraction, which is going to be called a hydrogen bond. Now, hydrogen bonds can occur between the hydrogen of one molecule and either a nitrogen, an oxygen, or a fluorine of another. That's because they have strong enough electronegativity that they will be have a strong enough negative dipole that they can attract those hydrogens. So this here would be our hydrogen bond. Notice we don't draw it as a solid line because it is not a bond that is set like a covalent bond. So water and hydrogen bonds, that's one of the things that makes water such a unique molecule. It makes it such a unique compound is because of these hydrogen bonds. It can hydrogen bond with itself. It doesn't even need another molecule. So since water is polar, it can attract other water molecules. This is known as cohesion. When water sticks to itself, that's cohesive forces. So that whole idea that raindrops are round, that's because water's sticking to itself and it's making it to a round bubble, right? Water drips off the end of a tap because it is sticking to itself. Well, water can also attract to other molecules via hydrogen bonds. This is known as adhesion. If you've ever walked home on a rainy day and you've had water kind of climb up the bottom of your pants, That's water adhering to your pants. So you see it sometimes in test tubes. It adheres to the side of the glass, forming the meniscus. Adhesion is between different molecules. So cohesion, two water molecules. Adhesion, water and another molecule, hydrogen bonding. We also have what's called London bonds or London forces. These are the weakest of all the intermolecular. It is between all molecules. The reason is those electrons are constantly moving. So at any given time, even if they're being shared equally, they might happen to be on the opposite side of that molecule. So it's a temporary unequal distribution of electrons, which allows those molecules to kind of, just for an instant, have a slight attraction to each other. It's called a London dispersion force. So here is the covalent bond. These red dotted lines represent the London dispersion forces, even though this is a non-polar molecule. And then we have van der Waals. This is between dipoles of any two molecules. Notice we have a specific name when it's hydrogen and nitrogen, oxygen, or fluorine involved, but if it's any other two dipoles, we call it a van der Waal. So because we have a slightly negative chlorine, slightly positive hydrogen, they have an attraction, dipole-dipole attraction, which is also called a van der Waal attraction.